I'm Stephen Foskett, the organizer of Tech Field Day, and the video you're about to watch is a Tech Field Day presentation from November of 2016. We have invited a panel of independent writers and speakers from across the internet and around the world to join us here in Silicon Valley to meet with various companies, discuss their products, and learn about their technologies. Right now, you're going to learn about Igneous Systems. You can find out more about them. You can find them on Twitter, Igneous.io. You can go to igneous.io. And if you'd like to learn more about this event, just go to techfieldday.com or view more videos like this at youtube.com/techfieldday.
I'm Jeff Hughes, CTO and co-founder of Igneous. And I want to dive into exactly that of what does this thing physically look like? What's the kind of configuration of it? And we saw the need to do things a little bit differently. So we call this our RatioPerfect Architecture. And I thought I'd start off with what kind of the state of the art looks like. This is Cisco UCS 3260. Beautiful piece of hardware. You know, this is for capacity-based, so it's 56 drives. Put some flash in. You can put 1 or 2 servers in there. We saw this sort of architecture developing quite a bit, particularly for these capacity-based workflows. I think some questions about 212 terabytes. That's a big chunk, but that's where we see a lot of these sort of machine-generated content going. And so we were looking to say, okay, how are we going to go cope with this from a capacity perspective? The challenge with that architecture really is that the construction of how disks and controllers get put together today, you kind of end up in one of 2 models for these worlds. You either have kind of the dual SAS model with, again, a bunch of drives behind that kind of dual SAS single head or two-headed controller, or you have more of the scale-out version, maybe some SATA connectivity, and then you have a lot of these very large, 40, 50, 60 plus drives behind a single CPU node. The problems we see on that is that, one, there's this challenge of I/O bottlenecks. How do I balance between how many drives I put behind a certain CPU, the controllers that are involved there, the front-end nodes that I put in front of this thing, and then the network connectivity out in front of it? You're playing a game of which one of these things do I need to optimize to hit both my workload or any sort of bottlenecks that are within that device. And so it was a challenge as an integrator of what we want to go do, and particularly because we were wanting to design around both capacity and performance. So it got more complicated. The other was this large fault domain. And this is a bit of a scar of just kind of the past, right? I've seen this fail quite a bit of, if you put 60 drives behind a single CPU node, that CPU or memory or something about that node is going to go wrong. And when it does, it's a huge hole. You've got to either go and replace that device really quickly or rebuild what could be potentially hundreds of terabytes stuck behind on perfectly good media behind that node. And so kind of to illustrate that, on the bottleneck side, there's all of these connections that you have to manage, and you've got like 2 fabrics. You're balancing what you want to go do with them. And on a failure side, this illustrates it perfectly. You could have a quarter of your whole installation go offline at any point in time, and that's a very big risk thing, especially if we want to maintain sort of our SLAs around both performance and availability of content. And so we had to step back and say, what are we going to go do for building our product where we wanted to go get this true service aspect? Well, starting off, you really need to get commodity. There's no way in which you're going to try to build something that is not based on commodity components today and be kind of competitive. The next is really reliability in numbers, because if you build something with commodity, you're not building the crazy, highly resilient hardware model. You're going to get it through just having a sheer number of devices that individually could go wrong, but as a mass stay very healthy. And then the third aspect is network centric, and this was really, we saw most of the software out there and being able to leverage software out there is more based on network as opposed to some sort of more esoteric interconnect out there. So we're talking about Ethernet here, essentially. And so we started off, as a startup does, of iterating. We started off with saying, hey, why don't we, as a physical platform, start with single CPU nodes with 12 drives, 10 gig connected to those, and start with maybe a minimum of 4 of them. You still kind of have a taste of that one unit could take out a quarter of your whole platform. But also on the other side, if I filled a whole rack full of this stuff, I've now got a ton of network to deal with, and it could become really cumbersome. And so we looked further, and we found a, maybe 4 drive sled. And you can get some lower end CPUs, maybe put an Atom core next to that as opposed to some Xeons and stuff like that. But this started to look really network heavy. You were individually plugging in a lot of those individual drives out there, individual sleds. And that just became even a bigger mess. But you can kind of see the trend line here. We started with 12, we went down to 4, and we're sitting there saying like, wow, why don't we just go to the logical conclusion of what's there, and why don't we build essentially a server per drive? This is really kind of the optimal balancing ratio. We can go build the exact right CPU for the exact right medium that we're going to go have out there. It's very network centric. You now have basically, just an Ethernet fabric as opposed to having both SATA or SAS or something there and having to debug what's going on with 2 things here. So from a software guy's perspective, I'm like, hey, this is a lot easier to deal with. I solved 1 problem instead of 2. And then it also brings up this question of, wow, we could go pass on the great economics of ARM onto potentially our customers and say, hey, we can start using these lower end CPUs that are actually developed in much higher volume than Intel CPUs and go do exactly that. And so we built effectively that. And I've got a couple examples here of a single CPU to drive ratio. And so I'll pass these around of a new platform that we built. So it's just commodity components. You can think of this as just a Raspberry Pi that we built. Nothing complicated here. It's just a CPU, flash, and memory. And on one side it has SATA, and on the other side it has Ethernet, essentially. And you can take the card off there if you want. It's a play model. So as you can see, it just fits in the shadow of a drive. No different than like an interposer would that did something like SAS to SATA. And as a result, we can actually take this and put it directly into what would look like a JBot. And in fact, we just get an off-the-shelf JBot where instead of having dual SAS controllers, we now have dual Ethernet switches within the box. And each of these each one of these little nanoservers, if you will, has 2 paths out any of the boxes. And you can really start to step back and say, hey, this starts to look like essentially what you'd have as a full rack of infrastructure, but shrunk down into 4U, is that you have redundant power, redundant switching, and 60 individual fault domains within one of those units. So if you return back to kind of the 2 problems I approached, the first was really that balancing act, is that now we're able to size correctly exactly how much CPU we want to go run on one of these things with whatever media we attach to it. And each one of those devices has direct full gigabit access today to the network at large. And now things have become a lot more interesting as to how we can do workflows across that full non-blocking network at that point. When one fails, it's nearly indistinguishable from the full set. Even in the minimum installation, you have 1 of 60 devices failing or whatnot. And so the fault domain problem becomes something that is very supportable even when we're not physically there. We don't have to have somebody within 4 hours to make sure that we get everything back up and running. We can actually have this be a fail-in-place architecture at this point in time where each one of these individually failing is not that big of a deal. So if you kind of step back and say, okay, what is this physical platform we run on? We can't just use these devices as terminating sort of protocols and front end and doing all the telemetry and the distributed software that runs across all these things isn't going to fit on just that little nanoserver. And so we combine a bit of both. So we have still just stateless x86 compute. So we'll still use some white boxes for kind of our top half software, if you will. Ethernet connectivity across all of this. And then nanoservers are the basis of kind of the storage platform, if you will. And then, we talked about a little bit about microservices. We can now run just stateless services, so things like protocol front ends, most of, a data path that I'll be talking about after this as well. Pretty much most of the high-end, high compute software, we can just run on basic, white boxes or even early on we talked about running it in VMs, but it's easier to just package this way. Scalable networking, we can get any sort of Ethernet we need to go manage how wide we want to go with this. And then we run anything stateful, we run on essentially these nanoservers, and we have a much more granular failure and the ability to do some interesting things, particularly in a peer-to-peer fashion between these. So we run software across the whole stack here. So I'll pause there if there's... This is a little bit different than what's usually you see on the shelf.
Interesting design.
Yep.
Yes.
So that's why your 212 chunk occurs, because you can't have 30 of these things in a box, essentially. Or you lose some of the resiliency that you would have then.
From an architecture perspective, we can actually go smaller. We picked a particular target to begin with, and for the applications that we were going after, the 60 was the right fit. That said, from an architecture perspective, we can absolutely shrink this down. You know, we can't go to a tenth of this. That kind of throws away things.
Yeah.
But could we go half? Potentially, yeah.
Yeah.
So it's really kind of a sizing question of how we go do that. The key is that, one, we can scale this completely horizontally, and all of our software is built to go do that, and I can talk about that some more. And similarly, we've separated the compute-heavy things from that. So there's always this game in most data paths and most applications even that you have, how do I scale my compute independently from my storage? And this was kind of our way of coming to that.
Mm-hmm. I mean, there's a SATA connector on the back of it through that chip. I mean, what is, you just then have, it's a JBot that's attached to it then that has some sort of single CPU that's running basically the logic for all those, is that correct?
So you can think of, within that box, there's like 60 of those, right? And then coming out the back is just two switches with 10 gig uplinks.
Okay.
You know, multiples of them. And so what you have now is that those nanoservers are directly connected to the network. As in, I can address them directly with software from my top-end nodes as well. So these can connect just directly across to any of those individual things, which is where it actually gets interesting, because now I have independent failure from my CPU from my disks, because any device within this picture can address any other device, which is not the case if you had either some sort of PCI network or PCIe sort of fabric, which you see out there very frequently, or on the other side, you know, some sort of SAS fabric or SATA fabric where you are tightly binding to a host a bunch of storage. Now we've loosely coupled the storage from the actual sort of software that mostly uses it.
What's the power demand in that appliance?
So that little card, it's only about 3 watts each. You can think of the JBot, it draws 1,500 watts or so. So it's mostly the drives.
Yeah.
You know, you could think of it from a profile perspective. When I ran the numbers early on, it's effectively equivalent to a JBot. Mm-hmm. You know, it's very low power, the little arm in there.
And you're using always desktop SATA drives?
We can flexibly use whatever media. I mean, since it's just SATA. For the product we use today, yeah, we ship with desktop drives, and very successful.
So that connector on the back looks like SATA, but it's essentially Ethernet?
Yeah, so it's an interesting play. It looks like a SATA or SAS connection, and it uses the SAS wires. So Ethernet and SAS, you can just send Ethernet signaling over what used to transfer SATA or SAS links. Is that it's effectively the same within the box. It's just a 2-wire differential pair.
It's like FCOE backwards. or SCSI, you know, instead of running your SCSI primitives over Ethernet, you're running your Ethernet primitives over SAS.
Yeah, it's just so that we're not confused, it's down at like the signaling level. So there's not any encapsulation or anything like that. It's literally electrically signaling Ethernet across those wires, if you will. Mm-hmm. So it is literally Ethernet coming out of that, not like encapsulated Ethernet in a SCSI frame or something like that.
You're just using the physical form factor to deliver it.
That's right. Yeah, it's the physical form factor, and then the switches instead of SAS controllers are going to pick up on that same thing. So you can think of the switches inside of there. They're 60 ports coming in, and then a few 10 gigs going out the other side. So it's very similar to just kind of a dumb Ethernet switch at that point.
So on your fail-in-place model, how many power supplies have you got in the back of each of those JBods? And also, do you have the ability within your management plane to define logically how those are, how physically they are located in a data center so you could survive, say, rack failures and those kind of things?
So our data path is certainly capable of taking advantage of data placement questions like that. It really comes down to how the customer wants to expect the service to be up. In one side, we're not trying to proclaim, the full cloud view of we're going to survive your data center and that sort of thing. But usually the applications are sitting right next to where we're putting this thing in. And so we're looking to be better than what is available to the application, if you will, mostly. As far as directly the question of power supplies, it's dual power supplies today, but that's just a strategy of the particular JBot that we have. We have full visibility of what's going on from those from a telemetry perspective. So if we see one of those things fail, we would obviously be out there to go replace that as you'd be down to a 1+0 kind of connectivity.
What was the primary I/O profile you're looking at for this?
So our primary workload is on kind of the very machine-generated, heavy, large content repository. So you can think
sequential writes.
Typically, yeah, that's what works well for something like object in S3. So you want to add something?
Yeah, just a couple of points. There was one question on Twitter that I can answer. But just before I do that, I want to point out one thing. The chassis that we use is completely off the shelf. We have not built anything. The only piece of IP from a hardware point of view is that nano controller that you guys got to see. In fact, we are using chassis that are shipped by ODMs to all the major cloud manufacturers. So we are drafting off on things that are already going out to the Google, Microsoft, Facebooks of the world. And that was a part of the sort of play there, if you will. The question on Twitter was, this kind of feels like the Seagate Kinetic drive. How is this different? When we got started, Jeff and we spent a lot of time looking at the Seagate Kinetic drive. We looked at the Open HGST drive and all of these things. Certainly, there was the architecture was elegant and we were attracted to it. At the end of the day, we chose to do what we did for, I'd say, 3 reasons. Number one is, especially with Seagate Kinetic, it was not an open platform. They exposed a key value API. They did not allow us to go run software on that. And that was very key, as you will see as Jeff goes into the last part of the presentation. So the second piece to that puzzle was it was too tightly integrated into the platform. Now you could only use a special purpose non-commodity drive coming from one or more vendor. What we have with this architecture is a decoupling of also the hardware, just like we talk about the software. We could go very, very quickly turn and use a next generation ARM processor for more CPU or a lot more power and then stick a bunch of SSDs behind that. We have a very flexible, extremely easy to iterate on architecture, which would not have been possible with an sort of something like a Seagate drive.
I'm assuming each one of those ARM nanoservers needs its own IP address?
Yes, it does, and it's got dual IP addresses, dual MACs, which was a third point, right? A large part of what we did and the way we built this is isolate the customer from having to deal with or manage with or look at it. There's, in fact, early on in the company, one of our board members made a comment that you guys think you're a storage company or an infrastructure company. You're really a networking company, and there's some truth to that.
Yeah, I think the one question that always comes up behind that is, it's actually all IPv6 though. So we're not asking for 120 addresses per box because I know that just wouldn't happen.
Well, even so, is the network that the drives are on isolated from the primary network?
We don't deploy that way today, but though we certainly could. So we just ask for a couple of ports on top of rack switches, and depending on how we want to, it's a conversation for the particular installation of what you want out of the network. So we can play that game, but we see that we can just leverage the network you already have in place, and it works pretty well.
So the Ethernet switch in that middle layer is the customer's normal Ethernet switch. It's not your Ethernet switch.
Correct.
Okay.
Good questions. So yeah, just to touch on kind of the takeaways here. One, we've got a scaling top half of the data path. We can put a lot of compute And you'll see why that matters. I'll talk a little bit more about the data path coming forward. But we can scale just commodity Intel hardware on the top. For resiliency and what that looks like, we have scaling bottom half that's very low compute and able to kind of be the capacity-oriented aspect that we were after. We can do very non-disruptive updates. To come back to the question that was on that, you can imagine that even when we have to do like an OS update on these individual drives, you're taking out one at a time, very, very low impact from end user flow and whatnot. And then really it was about the two problems we set out to solve, which is how do we balance these IO bottlenecks that are always out there, and that's where the RatioPerfect name kind of comes from, and then those fault domains as well, is that when these things do ultimately fail, we can go manage that. So.
About cooler answer than I expected.
It was pretty fun to build, you know. When we got started, we didn't set out to build a hardware platform. We set out to build a service, and this was just one of the side things that came out of it. Of the platform, we really had to go back to first principles and design the platform to support that end goal.
I'd like to sort of add to that one, which is if you look at what, again, we've taken a lot of inspiration from what the hyperscale guys are doing. And if you look at what these folks do, I like to say they suck in processed sand in one end and they spit out a service in the other end. But in between, they are not actually doing anything exotic. They are reassembling silicon in creative ways to solve this problem of sort of generating a service which requires very little human intervention. That's kind of what we have done. Sure, we've built a little computer, but it's ARM components, it's commodity drives, it's commodity chassis, and it's a software which ties it all together.